inexplicably jumps to a higher platform.
What the?
And an election recount is triggered, all because of the same invisible phenomenon that permeates the universe. On May 18th, 2003, voters in Belgium went to the polls. In many regions, voting was done on a computer, something the Belgians had been experimenting with for over a decade. But the system had a backup. Each voter would insert a magnetic card into the machine and make their selection on screen. Their vote was saved both to the computer and the magnetic card, which they dropped into a box for redundancy. Late that night, as the votes were being tabulated, one of the election officials detected a problem with the results from Schaerbeek, a municipality in central Brussels. Maria Vindevogel, a little-known candidate with her own party, received more votes than was mathematically possible. They knew this because of the way the preferential voting system works. So they took out the magnetic cards and started a recount.
Come on! What is this nonsense? Guys, I need some...
One by one, they fed each of them through the machines again. And after several hours, the recount was complete. The vote totals for every candidate were exactly the same as before, except for Maria Vindevogel. In her case, the... votes was less than the original by 4,096. So what went wrong? How had her original tally been inflated by over 4,000 votes? Computer experts were brought in to run extensive tests on the software. They combed through the code but could find no bugs. They got the computer that had made the initial erroneous tally and tested the hardware again and again, but they could not replicate the error. Everything about the hardware seemed to be in perfect working order. And this left only one possible explanation, and it is seriously weird. The clue comes from the excess number of votes Vindevogel received, 4,096. Computers work using binary, strings of zeros and ones, each corresponding to a power of 2. So somewhere inside the computer tabulating all the votes was a string of bits representing the number of votes Maria received. It started the day all zeros, and then as each vote for her came in, it would increment by 1. Physically, this is done by turning on a transistor for 1 and turning it off for 0. What's remarkable about the number 4096 is that it is exactly a power of 2, 2 to the power of 12. That is the 13th bit. So for Maria Vindevogel to receive an extra 4096 votes, only one thing needed to happen. The 13th bit had to flip from a 0 to a 1. But why would that happen? Computers work precisely because bits don't flip unless we want them to. Or do they? Looking into the problem, Belgian investigators found reports of similar issues from big computer companies starting in the 1970s. In 1978, Intel reported some strange errors popping up in their 16 kilobit dynamic random access memory, or DRAM. Ones would spontaneously flip to zeros with no apparent cause. The problem turned out to be the ceramic packaging the chip was encased in. With the demand for semiconductor packaging skyrocketing in the 1970s, a new manufacturing plant was constructed on the Green River in Colorado. Unfortunately, this site happened to be just downstream of an old uranium mill. Radioactive atoms made their way into the river and then into the ceramic packaging for Intel's microchips. Intel scientists investigating the problem found that even trace amounts of uranium and thorium in the ceramic were sufficient to cause problems. In their DRAM, memory was stored as the presence or absence of electrons in a semiconductor well. The alpha particles emitted by uranium and thorium were energetic and ionizing enough to create electron-hole pairs in the silicon. If an alpha particle struck in just the right place, it could create a large number of free charge carriers, causing electrons to accumulate in the well, flipping a 1 to a 0. This is known as a single event upset, a type of soft error. The error is soft because the device hasn't been damaged. The bit has changed, but you could erase it and rewrite it with no problems. Investigators exposed the chips to alpha emitters with different levels of activity, and just as you'd expect, they found the number of bit flips directly correlated with the number of alpha particles the chip had been exposed to. The reason this problem was identified in the 1970s was because chip components had been miniaturized to the point where a single alpha particle could produce enough charge to flip a bit. Immediately, these findings attracted a lot of attention. Before the paper was published, it was widely circulated in the industry, and as a result, chip manufacturers were a lot more careful to avoid radioactive materials when producing their microchips and packaging. Therefore, the bit flip that gave Maria Vindevogel 4,096 extra votes wasn't caused by natural radioactivity in the computer. So where did it come from? After Henri Becquerel discovered radioactivity with uranium in 1896, scientists sought a way to measure it. How radioactive were different materials? And one way to do this is with a gold leaf electrometer. When it's charged, the leaf is repelled, and you can measure the amount of charge by the angle of the leaf. Now, if ionizing radiation enters the chamber, it rips electrons off air molecules, creating positive and negative charges. Opposite charges are attracted to the leaf, discharging it over time. The higher the level of ionizing radiation, the faster the device discharges. In 1910, Theodore Wolff took his electrometer to the top of the Eiffel Tower. Since radioactivity was found in the soil and rocks of Earth, he expected that 300 meters up, the radiation would be just a few percent of the ground radiation. Instead, he found only a slight decrease. In 1911, Austrian physicist Victor Hess decided to take this experiment further, literally. He loaded electroscopes into the basket of a hydrogen balloon. In his first 2 flights, he observed the same thing as Wolff. Up to an altitude of 1,100 meters, both trips revealed no fundamental change in radiation compared to the values observed on the ground. But the next year, he conducted 7 balloon flights up to an altitude of 5,200 meters. And here, he discovered something remarkable. While there was an initial drop in radiation for the first several hundred meters, above 1 kilometer or so, the level increased with increasing altitude. At his maximum height, the level of radiation was several times greater than it was on the ground. The radiation appeared to be coming not from the Earth, but from the sky. Hess scheduled one of his balloon flights during a solar eclipse, and as the moon passed in front of the sun, he carefully watched his instruments. But the readings were unaffected. Even with the sun half covered, the level of radiation was the same. Since no influence of the eclipse on the penetrating radiation was noted, we conclude that even if a part of the radiation should be of cosmic origin, it hardly emanates from the sun. Victor Hess had discovered cosmic rays, high-energy radiation from space. But what were these rays exactly, and where were they coming from? Well, today we know they aren't electromagnetic rays, as many suspected, but particles. Around 90% are protons, 9% are helium nuclei, and 1% are heavier nuclei. Some of them are from the sun, but they have comparatively low energy. High-energy cosmic rays, moving very close to the speed of light, come from exploding stars, supernovae, in our own galaxy and in others. And the highest energy particles are thought to come from black holes, including the supermassive black holes at the centers of galaxies. But it's hard to pin down exactly where cosmic rays come from because, as charged particles, they're deflected by magnetic fields in space. So they can wind their way through the universe for billions of years. A cosmic ray detected on October 15th, 1991, had an energy of 51 joules. That is a single subatomic particle with the energy of a baseball going 100 kilometers per hour. For obvious reasons, it was dubbed the OMG particle. But primary cosmic rays like these don't make it down to Earth's surface. Instead, they collide with air molecules around 25 kilometers above the ground and create new particles, like pions. These collide and decay into other particles like neutrons, protons, muons, electrons, positrons, and photons, which in turn collide with other air molecules in one long cascade. So from a single primary cosmic ray comes a shower of particles streaming towards the Earth. It is one of these particles that investigators suspect struck a transistor in a computer in Belgium, flipping the 13th bit from a 0 to a 1 and giving Maria Vindevogel 4,096 extra votes.